So now we have seen where LTI systems come from. We've seen nonlinear models that turn into very well-behaved and pretty LTI systems, and we've seen nonlinear models that don't necessarily produce useful LTI models. But a lot of systems do produce useful LTI models, and it's really our most systematic way of designing controllers, and they are extremely useful. So even though there aren't that many bananas in the universe, a lot of things act like bananas. So what we're going to do now is we're going to start by understanding how these systems behave. So what I'm going to do in this lecture is I'm actually going to find the solutions to these systems. And once we have those solutions, we can start talking about how they behave. And we're going to start by simply ignoring the input and ignoring the output. So we're going to start by just saying that, let's say that I have x dot is ax. And at time t naught, this is the time when we wake up, we start somewhere. So this is the physical part of the system, not the thing that we bought actuators for, not the thing that we bought sensors for. It's just x dot is ax. Let's see what happens in that case. How does the system behave, or drift, if you will, when you're not messing with it? So we need to solve x dot is ax. Let's start with a scalar version of this, where x is just a number, right? So the scalar version I'm going to write as x dot is little ax. So this is a scalar version, and I start somewhere. Well, you may not know this, but if you've taken or seen differential equations, the solution to this differential equation is actually given by x of t is e to the a t minus t naught times x naught. So here, the professor shows up and says, oh, this is the solution to this differential equation. Now you clearly are critical thinking people who don't just accept anything the professor says. So what you want to do now is make sure that this is indeed correct. So how do you ensure that what someone feeds you, so here's a solution to a differential equation, how do you make sure that this is correct? How do we know? Well, the first thing you have to do is make sure that the initial conditions are right, meaning that my solution here actually respects this initial condition. So what I'm going to do is I'm just simply going to plug in t naught here and see what I get. Well, if I do that, I get x of t naught is e to the a t naught minus t naught times x naught. Well, this thing is 0, right? So I get e to the power 0 x naught, and e to the power 0 is always equal to 1. So the exponential evaluated at 0 is 1. So x of t naught is equal to x naught, which means that the initial condition is correct. So we're done with this. Now, clearly, we need to deal with this, right? We need to make sure that the dynamics is indeed correct. So now I'm going to take the time derivative of my proposed solution. So I'm going to take d dt of this thing and see what I get. Well, the time derivative of an exponential, all we do is we pull out the coefficient there. So we're going to pull out a and write an extra a there. That's all we do. And this is why exponentials are so wonderful. So the time derivative of x with respect to t is a times what we had here. Well, but this thing here, that's x, right? So the time derivative of x, my proposed x, is equal to a times x. Well, that's where we started, right? So what we now know is that the dynamics is correct as well. And if the initial conditions are right and the dynamics is right, we know, thanks to the existence and uniqueness of solutions to differential equations, that this is indeed the right solution. Now here is the kicker. For higher order systems, so now x is in Rn, we get the same solution. We have x dot is e to the a t minus t naught x naught here. Well, now we have this. X dot is the same thing. The only thing I did different was I wrote capital A instead of lowercase a. And the thing to keep in mind here is that this is what's called a matrix exponential instead of a scalar exponential, which looks kind of a little scary, but we're not scared of matrix exponentials. In fact, what we do is we look up the definition of an exponential. And an exponential, e to the at for scalars, well, it's simply this sum. This is the definition of what the exponential is. Well, here is just multiplications, and we can write multiplications for matrices as well. So the definition of a matrix exponential is just this sum. Now, it turns out that it's actually not that important to us to be able to compute matrix exponentials very much. However, we need to know where they come from, and they come from this sum. And the reason why this is useful, it actually allows us to compute the derivative of a matrix exponential. So let's take the derivative, the time derivative of this whole sum, right? So this is the sum here. Well, the first term that I'm going to do is I'm going to pull out the k equal to 0 term here. So then I get a to the power 0 times t to the power 0 divided by 0 factorial, which is 1. So this whole thing is actually equal to 1. And I'm going to take the time derivative of 1. Well, the time derivative of 1 is a big fat 0. So I'm going to pull out the first term. And then I'm going to take the derivative of the remaining terms with respect to t. So all I get here is I get an extra k. Well, now I can rewrite things. I can pull out an a and write everything in terms of k minus 1 instead of k here. But I'm summing from 1 to infinity. So if I shift my k now to 0 to infinity, I get back this thing. So what this means is that the time derivative of e to the at is simply big A times e to the at. So the matrix exponential behaves just like the scalar exponential. That's all I wanted to show with this slide, is that even though this looks a little awkward, we have these sums of matrix powers, all it means is that we can take derivative of matrix exponentials and trust that they behave just like in the scalar case. In fact, e to the a t minus t naught is such a fundamental object in linear systems theory that it has been given its own name. It's known as the state transition matrix. And sometimes I'm actually going to write big phi of t and t naught. And what we should then remember, and probably I will remind you of it, is that this is simply this matrix exponential. That's all it means, but it will show up quite a bit. Okay, x dot is ax. That means, in fact, that x of t is e to the big A t minus t naught x of t naught. Or in general, I can write it on this form. It's this state transition matrix, which we now know is just a fancier name for this matrix exponential. And it turns out that it doesn't matter if it's t naught or not. It's just whatever time tau, well, we just multiply what x was at that time tau times the state transition matrix. So this is simply code for x of t is e to the a t minus tau x at time tau. So the point is that we know what the solution to this equation actually is. And the way you would show that this is the solution is you would use the following two properties. And I encourage you to go home and do this. The first is the thing we just established, which is that the time derivative of phi is a times phi. The other is that phi tt is the identity. Well, phi tt, I just plug in a t here instead of t naught, so then I get e to the power 0. In the scalar case, that's 1. In the matrix case, that's the identity matrix. So that's the only difference when you go matrix. Fine. So now we actually have a controlled system. So we have x dot is ax plus bu. What happens? Well, again, the professor comes and says, oh, here's my claim. This is what I claim that the solution is. This looks like a mouthful, doesn't it? It doesn't look pleasant at all. Some stuff. In fact, this is the thing we had when we had no B matrices at all. And then we have this thing here that's, if you want to be picky, this is what's called a convolution. But we don't have to be calling it convolution. All we need to know is that, you know what, this is what we claim that the solution is. But how do we actually verify that this is correct? Well, we do exactly what we did before. We have to check the initial conditions and the dynamics. So let's plug in t naught here to see if we get the right thing. Then we get phi. Instead of t here, I'm going to write t naught. And then instead of t here and here, I'm going to write t naught and t naught. Okay, let's see what this is. Well, phi tt is equal to the identity matrix no matter what t is, right? So this is the identity. Now, here's an integral between t naught and t naught. So this is clearly 0 because I'm just taking the integral over this individual point. So this integral is 0. So what I have is I have that x of t naught is equal to what it should be, x of t naught. So we're going to declare success on the initial condition. Now, we need to deal with dynamics, and that's harder. First of all, we use the fact that if I take the derivative of this, I get an a out. So the first component is no big deal. But then we have this awkward object here. We have to take a derivative of an integral with respect to t when t shows up both here and here. And this is not a trivial thing. In fact, what you need to do is you need to use something known as Leibniz rule that tells us that if I have a general function here of t and tau, and I take the derivative of this thing with respect to t, well, first, this contribution here translates into plugging in, instead of tau here, I'm plugging in t, and then I'm just getting rid of the integral. That's the first piece. The other piece is I pull d dt inside the integral, and I have to take the derivative of this thing with respect to t. So this is technically what we have to do to compute this. So let's do that. Well, ftt, well, let's pull out this thing and evaluate it at tau equal to t o'clock. Then I get phi tt times bu of t, which in fact is simply bu of t, right? Because this thing is the identity matrix. And then I get the time derivative of this thing, or in other words, the derivative of this with respect to t. Well, I know that that's an a that I just have to pull out in the beginning. So this is a little bit of a mouthful. I realize too that. So take a deep breath and redo this computation just so that you believe it. But what happens when you've done this then is you can actually pull out the a and find that the time derivative of my proposed x is big A times this whole thing plus b times u. And now this whole thing is equal to the same thing here. So instead of writing this rather awkward big expression, I'm just going to write x of t here. Or, in other words, dx dt is ax plus bu, which is where we started. So we can declare success also on the dynamics. So to summarize, after all these push-ups, and I realized that today's lecture was a little bit of a, it was a little thorny in terms of all the integrals and derivatives. In fact, it's much thornier than anything we've ever seen before. The reason I needed to do it was not because I think you guys need to be world champions at applying Leibniz rule. I just want to be able to say the following, that if I have x dot is ax plus bu, y is cx, then I can write y of t as c times x of t, where we computed the solutions. We actually know that the output is given by this thing in yellow here. And you know what? Let's add another sweetheart to this. So all these push-ups just ended up with us being able to write explicitly what the solution is. Now, we're not going to be able to, or particularly interested in actually computing this at all, but we need to know it to move forward. So at the end of this application of Leibniz rule, what we ended up with was an expression for the output, or the state if you want to get rid of the C matrices, of this general LTI system. And phi here, the thing to remember is that phi, known as the state transition matrix, was simply given by this matrix exponential. What we're going to do now in the next lecture is see how does this actually translate into us being able to say things about how the system behaves. And in particular, we're going to look at stability questions.